All right, 4.1 scatter diagrams and correlation. So we'll look at all of these different things going on here today. All right, so just as a reminder, the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. So paying attention, what is our response variable? What is our explanatory variable moving forward? Okay. All right, so scatter diagrams. So a scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. We typically see this on our XY plane when we plot points on this. It looks like a scatter diagram when we just do points. Okay. So our first example here, we have a golf pro. We want to look at the club head speed of a golf club compared to the distance the ball will travel on that club head speed. Okay, and so they did some data and they came up with these. So at 100 miles per hour club head speed, the distance was 257 yards, and so forth, all the way down on those. And so we would just plot those points. Our club head speed would go on our x-axis, our distance would go on our y-axis. And so we would end up with a graph that looks like this, okay? And so that's going to be just comparing those things. Your homework is going to be multiple choice, so you want to be able to pick out those points from that and be able to tell what's going on there when you're looking at those pieces. All right, so scatter diagrams show the type of relation that exists between two variables. And so we want to distinguish whether they imply linear, nonlinear, or no relation. That's one of our goals. And so if it's linear, that means that our points pretty much make the shape of a line. They may not be a straight line specifically, but they kind of give us that shape. And so we can see here in these that this first one is kind of making that shape of a line, as is the second one. And so we would call those linear. Now these others make a shape, but they're not a line, so it would be nonlinear, as is our D. It kind of makes this shape, but that's not a straight line. Now our last one doesn't have a relation because it's really hard to tell what's going on there with those pieces. Okay. All right, now if it's linear and makes a straight line, we can have positive or negative association. And so that's what these definitions are. The best way is to really see the pictures. So let's go back here with those two linears with that. So if it moves up as it goes left to right, we call that positive. If it goes down, we call that negative on those, okay? So kind of uphill, downhill as we move left to right for those, for positive and negative. And we wanted, that shows us a few things there. Okay. All right, so now we want to be able to look at the properties for those, okay? So never mislead our reader with those. And we have what's called the linear correlation coefficient, okay? And so we're going to mainly focus on R because we're going to be looking at samples. So when they talk about R here, we're looking at the sample correlation coefficient. So we want to be looking for that for these pieces. All right, so of course there is this long formula, but we're going to look at how the calculator is going to do that with us on those, okay? And so we don't have to break those things down because it's going to get pretty nasty, as you can see with these, okay? Now a few things before we get into that. There are some properties that we want to pay attention to. The linear correlation coefficient is always between -1 and +1. Now a +1 means a perfectly straight positive line. All of our dots are lined up. We could put a ruler on them. They would make a line, and it would be positive. -1 as well as a straight line. So ones mean straight lines. All of our dots line up. Positive means a positive correlation. It's going uphill. Negative means it's going downhill with those. Now the closer to 1 means the closer to a straight line. The closer to 0 means no correlation. So if we have R equals 0, we don't have a linear correlation. All right. Now, it doesn't mean there's no relation, but just not linear for those things. Okay. All right, so here are some examples of that. So you can see in part A, we could pretty much put a ruler through that. That is going up positive, and that would be a straight line. That's a 1. Whereas in part B and C, those still are going uphill, but they're not as strong. They're a little more spread out. I can't connect every point into a straight line with it. I can draw a straight line through it, but it's not going to hit every single point on those. And so that's why they're different numbers. Now, part B is a 0.9 because they're real closely related to each other and moving up, whereas C is a 0.4 because they're a lot further apart on those pieces. And then D, E, and F are just the negatives of all of those. Now you can see in G and H, G is all over the map. I could be drawing lines in all kinds of directions there. We're not sure what's happening with that piece. And so there's no relation at all there. Whereas in H, it gives us that hill shape. It's not a straight line. So there's a relation of some sort. It's just not linear. And so we would say that R is close to 0. All right, so for instance here, we would look at this. I would say that this is probably a 0.8, 0.9, somewhere in there on those. Okay. All right, so let's look at this one. So we've got our data. We want to see what is R. We want to calculate that piece for us, okay? And so we want to turn our calculator on here, clear out that old information that we have on those, okay? All right, now the first thing before I get into this, we need to make sure that our diagnostics is turned on so that we get the proper numbers moving forward, okay? If this is not on, we're not going to get all the information that our calculator is programmed to do. Okay, so let's do that. So to get our diagnostics on, first we need to go into our catalog. Well, notice our catalog down here on 0 it is in blue. So we hit the second and then 0. And we're in our catalog. And this is all the different programs, different things that the calculator will do. Whether we know what they mean or anything, it's all the different stuff in there. Okay. Now we need to turn our diagnostic on. Okay, so diagnostic on. All right, and so I'm going to do a little shortcut here. It says A. You see this little alpha up here? That means that I can go down by letter. And so diagnostic starts with a D. So I can hit that D there, and it's going to drop me down to D. And so we want to go to down to where it says diagnostic on. Okay? So notice my arrow again is on diagnostic on. So diagnostic on. And I'm going to press enter and enter again so that it's on. So we need to make sure in order to find R that we do that at the very beginning so that we get all of our information. Okay? All right, now that we've done that, we're going to clear that out. So let's go into our table. So we're going to go to Stat, number 1, and we're going to fill in our table of values. Well, it looks like I've already got that in there, so I don't have to type those in. But at this point, you would type in those numbers there. Our X goes into L1, or Y goes into L2. Okay, so once you get those into L1 and L2, now we're going to go back to Stat, and we're going to move over to Calc. And this time we're going to go down to number 4, linear regression. Okay, and so we want to use that. And we're going to hit enter. Now, if you're on the 83, you should just be able to hit enter again, and it's going to calculate what you need. On my 84, I've got L1 and L2 listed, so I just need to go down and calculate to get what I need there. Okay? And so we come up with an R of negative 0.9456. Okay? Which makes sense because when we look at our graph here on this, most of our points are lined up pretty well, and so I would assume that we could get a pretty close line there on those. But we do have this one little one out here that says it's not a straight line. It's not all of them are lined up with those, but it is going down as well. And so this R makes sense. Okay, so they go through all the handwork here. and they come up with the same number that we did. Okay, with those. So as you can see, that calculator is going to help us get a lot better answer when we're doing those things. Okay, so make sure that you have that down. All right, so the next little example here, we're not going to put it in the calculator, but they went and did our club head speed. So back on the first table there, and they came up with a correlation of 0.939, essentially, there on that, okay, for those pieces. So they used Excel to do that. So there are many programs, again, that can do these things for us. So we would go back and put that into L1, L2, again, go to our linear regression to do those, okay? All right, so the next thing is testing for a linear relation, okay? And so if a correlation coefficient is positive and greater than the critical value, they are positively associated. If it's negative and less than the opposite of the critical value, then they are negatively associated, okay? All right, so if we're looking at the club head speed there, let me clear that so we don't get any confusion. Club head speed, we just said a moment ago that they got 0.939 for their correlation coefficient. So we do the absolute value of that, and it's still 0.939. Now, we would compare that to Table 2. Now, Table 2 will be given to you in the problems where they ask. It's going to say the critical values. Now, they got N as 8 because there were 8 items on the table, 8 points that they were graphing on there, okay? So if we were to go back to that table, you would see that there are 8 points, 8 x values, so to speak, and so they would compare that. So since 8 gave us a critical value of 0.707, our 0.393 is greater than that, and therefore there is a positive association, okay? All right, now we do have to be careful. If data is used in observational studies, we cannot conclude that two correlated variables have a causal relationship. We have to make sure that we talk about our lurking variables that could be related to both the explanatory and response variable. All right, so for example, as air conditioning bills increase, so does crime rate. So does that mean that folks should turn off their ACs to reduce crime? No. It just means that when it's warmer outside, people are more likely to commit crimes. Compared to when it's cold, people don't want to get out and commit the crime in the first place with those, okay? It's just kind of the way it is. It happens to be there, all right? All right, so here is another example. It says colas tend to replace healthier beverages, and they contain caffeine, phosphoric acid, and so forth, okay? And they want to know if there is association between cola consumption and lower bone density in women. All right, and so they collected this data, number of colas per week, and the bone mineral density. And so here it looks as if there is a negative linear relation on this based on the information, okay? All right, so can they? Well, first of all, let's look at our lurking variables in those, okay? So they did a cohort studies, and they got to take into effect age, body mass, weight, or height, smoking, average daily intake of alcohol, calcium, caffeine. All these different things can do those. So we can say that there is an association with lower bone mineral density because of the lurking variables, but they can't say that it causes it. So those things are very important to recognize when you're doing those things. Is there maybe an association? Yes, but is it the actual cause because of all the lurking variables? Possibly not. All right, so those are the things that you're going to need there for 4.1.